We are going to talk to you today about our endohedral fullerenes. Now, these are a really interesting and exciting material with some very special properties that we're able to exploit in our experiments here in the lab at Lancaster University. Now, they also happen to be the most expensive substance on Earth, apart from antimatter, but we don't count that. Now, we've got about 5 milligrams in this solution. If we had a full gram, it would be worth around £200 million.
So endohedral fullerenes are atoms or molecules trapped in carbon cages. This specific one is 15N in C60, which means there are alone nitrogen-15 atoms in cages of 60 carbon atoms.
Now, if you've seen our previous video on our EPR spectrometer, you'll know that this is the molecule that we're using for our electron paramagnetic resonance experiments.
So we're going to talk to you today about how these molecules are produced, what their special properties are, and what exactly we're doing with them here. Endohedral fullerenes are only produced in one place, by Designer Carbon Materials in Oxford. The reason why they're such an expensive material is that the process to make them is very difficult, involving both ion implantation and high-pressure liquid chromatography.
Now, what happens in that process is that the fullerenes, the carbon-60, is first vaporised and then deposited onto a copper sheet. It's then bombarded with atoms of nitrogen-15, and some of them go inside the carbon-60 cages. But the penetration rate is very low, about 0.01%. So the high-pressure liquid chromatography separates the endohedral fullerenes, that's those containing a nitrogen atom, from the empty fullerene cages. And it does so by utilising tiny differences in polarisability and molecular weight. Essentially, the difference between the two is the mass of a single nitrogen atom.
In order to get a high purity of the endohedral fullerenes, this must be repeated many times, making the overall process long and intensive, hence the high cost.
The synthesis of NNC60 was first reported by Murphy et al. In 1996. They deduced that the EPR signal from the molecule would correspond only to the paramagnetic nitrogen-15 in the centre because the C60 cage is diamagnetic.
This is actually the first time that nitrogen could be studied as a lone atom, because in ambient conditions it is usually too reactive. However, the 3 unpaired electrons that give it this high reactivity also allow for clear EPR signals.
The C60 cage isolates the nitrogen atom in the centre, meaning that the molecule retains the total electron spin 3/2, attributable only to that nitrogen atom.
But before we go into the quantum physics, why are we using this molecule in the first place? Here to answer that question is the leader of our research group, Professor Edward Laird.
We are developing a portable atomic clock based on endohedral fullerene molecules. Clocks are everywhere. There are probably more clocks in the world than there are people. They're important whenever you have radio communication, radar, and in particular for navigation. Let me give you one example of why precise and portable clocks are so important. This is for navigation using the Global Positioning System. Now, the way that GPS works is that the sky contains GPS satellites that are on precisely defined orbits, which means that they know where they are at any particular time. What your GPS receiver has to do is to work out from signals, radio signals coming from those satellites, precisely where you are. And this is how it does it. Let's suppose your receiver down here can receive signals from 2 satellites here and here. What it can do is to compare the arrival times of the 2 satellites, and if it sees that the signal coming from this satellite arrives before the signal from this satellite, that means it must be closer to this one. Because it knows the speed of light, if it can measure that difference in time precisely, it can locate your position to within a meter or so. Now, clearly we need a clock to precisely compare the arrival times of these 2 signals, but in fact an accurate clock is even more important than that, because an accurate clock can also precisely measure frequencies. The problem with the GPS signal is that it's extremely weak. The only way that we can detect it is to lock on to the frequency of the GPS signal and ignore everything at all other frequencies. and therefore the most accurate GPS receivers, the one that can lock quickly to the GPS signal, also have to contain very precise clocks. The most precise clocks will be atomic clocks. Let me tell you how an atomic clock works. Consider an ordinary clock first of all. My wristwatch contains a quartz tuning fork that vibrates at a particular frequency, and by counting those vibrations, my watch can keep track of time. This is pretty good, but quartz tuning forks are not perfect. Firstly, every one that you make vibrates at a slightly different frequency, and secondly, as they age, their frequencies drift as well. The most accurate clocks use the absorption frequencies of atoms, and because all atoms are exactly the same, and because they don't change with time, this lets you generate a time signal as precise as anything that you can do. This is how it works. We have an oscillator, and it generates a radio wave, and we send that radio wave into a cell containing atoms. If we hit the precise absorption frequency of the atoms, some of that energy will get absorbed, and so the radio wave that gets transmitted will become weaker, and we can detect that. So we can tell whether the oscillation frequency here matches the absorption frequency of the atoms. We can also tell whether it's too high or too low. So what the detector does is to send a feedback signal back to the oscillator that tells it to adjust its frequency to lock it to the absorption frequency of the atoms. And when we have our oscillator running inside a feedback loop like this, its frequency now doesn't change. It's always locked to the atomic frequency, and this lets you generate an extremely precise timing signal. That's how an atomic clock works.
The atomic clock uses the electron paramagnetic resonance signal from the sample. We investigate this using an EPR spectrometer such as this one. You can see that we have the fullerene sample in its tube in the spectrometer cavity. If you'd like to know the full details of this setup and how it works, you can check out our video on the EPR spectrometer on the channel. So this is what that endohedral fullerene actually looks like on a molecular level. You can see we've got the 60 carbon atoms arranged in that Buckminster fullerene shape with a single nitrogen in the middle.
That nitrogen atom spends most of its time in the centre of the molecule, with its electron cloud restricted by the carbon-60 cage.
So let's talk about the quantum physics of this molecule and what makes it so suitable for our experiments.
So firstly, nitrogen has 3 unpaired electrons. That means that for a given amount of material, it has a relatively high spin count, which gives you more bang for your buck, if you will. You get a stronger EPR signal from the sample.
To determine the EPR spectrum, we need to consider several couplings that happen within the molecule. These can cause splitting to the energy levels and so must be accounted for in the Hamiltonian.
So these can include spin-orbit coupling, which is a coupling of the spin angular momentum and the orbital angular momentum of the electron. Hyperfine coupling, which includes the Fermi contact interaction and the magnetic dipole coupling. These are couplings between the electron and the nucleus. We also have zero field splitting, also called dipole-dipole splitting, which is the coupling of independent electrons via their magnetic dipoles. And finally, quadrupolar coupling, which is a coupling which occurs for nuclei of spin greater than 1/2 with a local electric field gradient.
The less of these couplings that you have, the simpler your Hamiltonian is, and this means that it's much easier to get a clear and sharp EPR signal.
Now fortunately, for 15NC60, we only need to be concerned with hyperfine coupling. The extra neutron in the nucleus of nitrogen-15 means that the nuclear spin is 1/2, and so there's no quadrupolar coupling.
Furthermore, we can neglect zero field splitting due to the spherical symmetry of the molecule. And there is also no spin-orbit coupling, as this is dependent on the total angular momentum of the electrons, which in this case is 0.
And finally, the unpaired electrons in nitrogen are in p orbitals, and p orbitals have nodes at the origin, meaning that there's no Fermi contact interaction. So this leaves us with a nice simple Hamiltonian for the molecule, containing only Zeeman splitting terms and an isotropic hyperfine coupling term. So in a Z-facing applied magnetic field, that Hamiltonian looks like this.
Here, Ge and Gn are the electron and nuclear G factors. μb and μn are the Bohr and nuclear magnetons. A is the isotropic hyperfine constant. B0 is the applied magnetic field strength. S hat and I hat are the electron and nuclear spin operators, and Sz and Iz are the corresponding spin components in the z direction. We can re-express the nuclear magnetic moment using the Bohr magneton so that Gi mu b is equal to Gn mu n. The Hamiltonian can then be rewritten. From this Hamiltonian, the energy eigenvalues can then be extracted. Here, G tot equals Ge plus Gi.
So we can plot the energy eigenvalues against applied magnetic field strength, and when we do that, it looks like this. It's interesting to note that the negative value of the nuclear G factor leads to a negative value of the hyperfine constant A and an inverted energy manifold. So the bottom 5 eigenvalue lines correspond to the quantum number F equals 2, whereas the upper 3 correspond to F equals 1. The clock transition is shown by the black double arrow, and at higher fields you can see that the Zeeman splitting dominates and the levels become 4 sets of hyperfine split doublets.
We can look at any allowed transitions between two energy levels, but in particular we want to look at parallel mode transitions, which occur when the driving magnetic field and the static magnetic field are parallel to one another.
And the reason we want to look at parallel mode transitions is because that's where our clock transition occurs. So the lines on this graph show the values of field and frequency at which transitions occur with respect to the energy levels. As you can see, the clock transition occurs at the bottom of the parabola, which relates to transitions between energy levels 6 and 7 from the manifold. The clock transition itself occurs at an anti-crossing between these two energy levels. The reason such transitions are called clock transitions are because they're particularly suitable for use in an atomic clock. The reason for this can be seen from the graph. The gradient of frequency with respect to magnetic field is 0 at the bottom of the parabola. This means that any device using the frequency corresponding to that point on the parabola as the reference frequency for an atomic clock will be relatively insensitive to small fluctuations in magnetic field, in this case to approximately first order. And this makes the clock much more resilient and stable in real-world conditions.
The clock transition occurs at a frequency around 39 MHz, which is a radio frequency. It also occurs at low magnetic field, around 0.8 milletesla. This means that for our atomic clock, we can use relatively simple radio frequency electronics and also a low power electromagnet. This contrasts to current chip-scale atomic clocks, which have to use more complex, fragile and power-hungry components such as lasers and vapor cells. Essentially, this means we can build an atomic clock that is smaller, more robust and uses less power.
The EPR spectrum of 15 NEC60 has a narrow frequency domain line width, which sharpens toward the clock transition. What this means in practice in a clock setup is that if there's a small frequency drift in the local oscillator producing the driving signal, there's a large change in the absorption magnitude of the sample, and this leads to a faster, more efficient error correction response.
One final benefit of using this material is that we can dissolve it in carbon disulfide, leaving us with a liquid sample at room temperature. This is very easy to work with, both in terms of our experiments and also in terms of the greater atomic clock assembly.
So let's have a look at some of the data that we've obtained in our EPR experiments whilst working towards a prototype endohedral fullerene atomic clock. The blue horizontal lines here are measurements taken whilst illuminating the sample with a signal of fixed frequency while sweeping the magnetic field. The curves are Lorentzian first derivatives and are the resonances caused by absorption of the energy of the signal by the endohedral fullerene sample. The red line is the clock parabola and appears here as a fit to the data using the centre points of the resonance curves. This shows the frequencies at which transitions occur with respect to the applied magnetic field strength and is as expected from our theoretical prediction shown earlier. The clock transition is visible right at the bottom of the parabola as expected. These are the expected transition frequencies at low and zero applied field plotted using Python with the values of the hyperfine constant calculated from the previous data. Here a negative magnetic field B0 means a reversal in the Z direction. We set up the spectrometer to measure a small section here in the centre around the zero of B0, using a magnetically shielded environment. The idea was to test the prediction and to obtain a more precise value for the hyperfine constant. And finally, here are those measurements in the form of a 2D colour plot. The black lines are fits to the data from which we were able to extract a high precision value for the hyperfine constant, which we intend to publish soon.
As you can see, this is a very interesting molecule with a lot of special properties and a lot of potential, especially when it comes to creating a new atomic clock. So for us, it's worth that high price tag.
Thanks for watching this video. We hope you found it interesting and informative. If you've got any questions or any thoughts about the molecule or anything related to it, whack them in the comments. We always love to hear from people.
And if you did enjoy this video, check out all the others on the channel, and we are also putting out a lot of new content soon.
Thanks for watching.